Okay, great. Thanks for that introduction. Appreciate it, Katie. And hopefully you guys can see my screen okay. So as Katie mentioned, I'm Jason Riveri, and today we're going to chat about two new exciting features focusing on security within PanOS 11. Specifically, advanced Wildfire and improvements to advanced threat prevention. So we'll go through the new features included in these services, as well as get into some very technical details on how they work. So let's start with advanced Wildfire. Oops, sorry. So over the last year, we've seen some dramatic developments in the malware space. First, attackers have greater accessibility to malware. In years past, we've seen a steady speed increase, but this has actually gotten significantly faster in the last year. Primarily, we attribute this growth to a number of as-a-service offerings. Think of malware as a service, ransomware as a service, etc. This really lowers the technical bar for bad actors to deploy malware campaigns. These offerings enable criminals to not only increase their numbers of attacks, but allows them to create different variations and new malware variants. Second, we're seeing a layering of evasion techniques. So these new types of modern malware are more sophisticated, employing various evasion techniques to bypass detection. So our threat researchers have seen more and more malware using evasion techniques, sometimes 3 types of evasion techniques within a single file, or in some cases, layering 6 or more evasion techniques to avoid detection. So if we look at some real world examples of them, these evasion techniques, these 3 are kind of among the top malware families tracked by CISA. We'll start with Quackbot. Quackbot was originally a modular banking Trojan used primarily by financially motivated actors. We've seen Quackbot leveraging process injection techniques such as thread local storage and process hollowing, as well as code signing, which is really interesting. Next is LokiBot. This started off really as an information stealer, but it's evolved into a multi-stage remote access Trojan, or RAT, sometimes leveraging 3 different types of evasion techniques, such as reflective code loading, base64 encoded packing, etc. Ursnif is a financially motivated malware that has really evolved a lot in the last 10 years. They incorporate a lot of highly sophisticated memory-only evasion techniques, such as, again, process injection, thread local storage, and process hollowing. So these malware families have been around for quite a while, but what's alarming is that they've evolved and to the point where detecting them requires employing advanced sandboxing techniques, such as memory analysis. And these are just a few examples of the way modern malware has evolved beyond the detection capabilities of a traditional sandbox. So how do we protect against these kinds of threats? What kind of capabilities do we need in our analysis tools in order to detect and protect against these advanced malware techniques? So first, we need to be able to detect memory resident malware. Malware is no longer tied directly to a file, but it could actually be malicious commands that run only in memory. So we really need to analyze the memory. Next, we need to uncover latent behavior. So we can't allow malware detection to simply time out and miss a detection because the malware was quote unquote sleeping. Finally, we need to be able to do these 2 things without being detected by the malware. So in other words, we need to have some sort of stealthy observation technique so malware is able to fully execute and we can analyze its behavior. And that's where advanced Wildfire comes in. It's the industry's largest malware analysis engine, and it's capable of preventing the most evasive threats with unmatched speed and scale. We have a completely new infrastructure where we're able to do hookless inspections of malware behavior in memory and get an in-depth understanding of the malware's DNA, ranging from its intent, the target, evasion techniques, dependencies, etc. Being able to perform these advanced analysis techniques requires significant additional infrastructure with access to an unlimited supply of compute and storage to detect evasive malware quickly and on a global scale. The addition of these new advanced wildfire detection techniques results in further detection efficacy improvements. From the research that we've been doing, we've observed a 26% increase in the detection efficacy on files that were previously deemed to be benign because they were highly evasive. So let's walk through the journey of a piece of malware. So an unknown file is usually observed by one of our enforcement points. This could be a next-gen firewall, VM series, cloud, endpoint, Cortex XDR, maybe even from a third-party feed. All these are connected into advanced wildfire. The file will go through the enforcement point, let's say a firewall, and it gets checked if it's a known or an unknown variant of known malware. And if it is, we just block it. If the file is deemed to be unknown, then it's sent to the cloud to go through a series of analysis. That starts with static analysis and machine learning. Dynamic analysis is performed to extract further information from the sample, and if the confidence score on the sample's verdict is still low, it then goes into AWS advanced detections. All these detection engines can find a malicious characteristic of a file at any given time and automatically generate protections against the file and IOCs observed during the analysis. The signatures are then delivered in near real time back to the enforcement points all over the world, making advanced wildfire signature delivery one of the fastest malware protection mechanisms available on the market, 60 times faster than our nearest competitor. The new AWF detection capabilities are the result of years of malware reverse engineering and research coined by 10 new patents delivered on top of a completely new infrastructure. The Advanced Wildfire Cloud is deployed in 3 different countries in 10 different locations and has 17 internationally recognizable certifications. So built on over 10 years of innovation, Advanced Wildfire is the industry's largest malware prevention engine. It stops over 99% of known and unknown malware. Advanced Wildfire is also the industry's only network security product to determine an additional 26% of highly evasive modern malware at scale with new patented detection techniques. So let's get into some more technical details and dig into these new techniques that we have in Advanced Wildfire. So malware creators have, for a long time, been trying to avoid detection by sandbox solutions. It's very much a cat and mouse game. Because traditional sandboxes used well-known virtual environments for analysis, threat actors figured out that they can check the environment in which the malware is executed to determine whether the malware is being analyzed. Characteristics checked may include the underlying hardware, such as the number of CPUs, amount of RAM allocated, even things like screen resolution, or for more advanced malware, user interactions. Attackers can use many ways to obfuscate their malware and bypass detection. These include techniques such as encoding, encryption, compression, packing, etc. Many of these same techniques are used by legitimate programs, such as packers, to protect an application's source code and trade secrets. So when Wildfire analyzes malicious content, it frequently finds multiple layers and types of obfuscation in a single file. When obfuscation is removed from the code, it may reveal new code that also needs to be analyzed. If more obfuscation is found, the whole process needs to repeat. Obfuscation is not always malicious, but it can make detecting malware very challenging. Excuse me. Finally, we've observed that highly evasive malware can be memory resident, essentially fileless malware that is often a script or an injection. After being written into a target computer's RAM, memory resident malware is able to perform its malicious activities. For example, you can go to a malicious website and the site might automatically run a script that forces malicious code into your computer's RAM. Because there's no file containing the memory resident malware, it's challenging to detect using traditional static and dynamic analysis approaches. The Advanced Wildfire Dynamic Analysis platform uses out-of-guessed virtual memory introspection and memory analysis to monitor and detect highly evasive malware. This is accomplished without the use of in-guessed components that can be detected by the malware or that could otherwise influence analysis results. The platform was designed to be highly configurable and rapidly expandable. Being a proprietary built hypervisor, Advanced Wildfire Analysis withstands malware environmental checks and does not fall victim to exploitation of common VM backdoor interfaces. The new AWF virtual machine introspection allows us to monitor all phases of the file analysis, including loading analysis modules, configuring out-of-guess monitoring, as well as observing OS-level API calls. We can also capture memory snapshots and perform post-processing on those results very quickly. So memory analysis is extremely useful for malware detection. And we need to be able to look at the deltas in the memory for key points of execution and extract meaningful information and artifacts from them. So AWF introduces a completely new patented malware analysis technique, Intelligent Runtime Memory Analysis, or what we call IRMA. This platform is built on top of a newly introduced cloud infrastructure that achieves detection efficacy and speed at Wildfire's scale. Memory capture is a pretty common technique used for malware analysis. So let's kind of compare IRMA to other traditionally used techniques shown at the bottom of the slide here. So on the bottom left is the continuous memory capture technique employed by some traditional sandbox solutions. This technique, while very powerful, has a couple of problems. Two of the most common problems are the frequency of capture and the noise in the results. Because memory snapshots are taken continuously during the entire analysis, separating the interesting events from the noise to get valid results places a high demand on the resources of the underlying sandbox solution. In addition, processing large numbers of memory snapshots is a time-sensitive process and leads to equally long verdict determination. To solve the shortcomings of continuous memory capture, the malware detection industry came up with an alternative approach, intermittent memory capture. So this method takes memory snapshots at specific times or checkpoints, usually at the beginning, middle, and at the end of malware analysis. While scalable and less dependent on the underlying system performance, this method does not improve detection efficacy as it can easily miss important memory events. Intelligent runtime memory analysis achieves unmatched efficacy and speed. AWF tracks malicious activity during runtime and creates memory captures when something interesting happens, all while requiring fewer resources to do so than some other techniques. So this happens in near real time. And as memory snapshots are analyzed, protections are automatically generated and delivered to the enforcement points even before full analysis is concluded. So here's a visualization of the intelligent runtime memory analysis. AWF's IRMA captures memory snapshots during, like I said, interesting events, such as an API call that might be suspicious or indicative of suspicious behavior. These individual memory snapshots are building a memory snapshot timeline that can be used to review the memory of the system at various points in the analysis. That allows us to identify things such as executable code that was unpacked, PE modules, etc. Memory capture also contains a variety of other useful artifacts, such as memory permissions, OS structure modifications, and API information. These artifacts are used to create behaviors and support verdict determination. What is novel about AWF's approach is the processing. AWF doesn't wait until the end of the sample analysis execution, but rather the memory snapshots are processed in runtime and can generate signatures immediately if malicious behavior is observed. So another innovation introduced in Advanced Wildfire is automatic payload extraction. As mentioned, it's increasingly common for malware authors to obfuscate their payloads. While packing is nothing new, It becomes problematic when used in combination with other evasion strategies because there's no static or dynamic data useful for an accurate detection. And there's really an infinite combination of strategies for encoding, compressing, encrypting, or even downloading additional stages for execution. The ability to craft signatures for these payloads is obviously an important way that our analysis can catch lots of different malware components from frameworks like Cobalt Strike. If we can catch them in memory, it ultimately doesn't matter if the malware decides not to execute. So this simplified diagram shows an example of what we might see in a couple of stages that were never present at the initial executable file. So on the left-hand side, we see a pattern of the shellcode stage. A common pattern for malware authors taking this approach is to dynamically resolve all of the function pointers into a table for ease of access. On the right side, we see that the latter stage is an example of a well-formed executable. Some malware stages or payloads are well-formed executables. They can be loaded by the OS via the system API, or the malware author might use their own PE loader if they're trying to be stealthy to avoid calling any system APIs to do this for them. PE files continue to be the most malicious file type. Sorry. They often require external dependencies to properly execute during analysis. Think, needing zip.dll. We see upwards of 30 to 35,000 unique samples per day, requiring additional libraries to execute. And if the dependencies are not present, dynamic analysis can't run because required libraries are not found in the base analysis disk image. This means no detection by dynamic analysis because the files processes are never created. Advanced Wildfire inspects the PE headers for dependencies, or what are called imports. These tables define a set of libraries or DLLs and the list of functions required within each library. So at execution load time, before the actual execution, the Wildfire Windows loader will ensure all libraries are loaded. All import addresses are written into the import address table to make them available for the code to execute while allowing dynamic analysis to complete. So with the boom of malware as a service offerings, we've observed more malware being auto-generated. AWF's memory analysis capabilities include malware configuration file analysis. Malware configurations consist of parameters embedded in each malware sample, and they can include details like the encryption keys used, or some identifiers on who authored the malware or campaign identifiers. They can include command and control addresses, paths for persistence within the operating system, all kinds of things. So the malware configuration includes context details like process and snapshot information. So in this example on the right, we see the encryption key, some campaign identifiers, as well as command and control addresses. So this information can be extracted even in an instance where the malware sample fails to properly detonate and can reveal actionable artifacts that may not have been observed during an execution, such as alternate C2 addresses. All this information is very, very valuable from a network security standpoint and is leveraged within advanced threat prevention. So when it comes to network-based attacks, there are a few things that really stand out. Again, we've noticed an increase in the use of automation. Adversaries are leveraging readily available tooling and public cloud infrastructure to distribute malware and host their C2 servers. Defenders can't rely specifically on IOC feeds, like blocking just IPs, URLs, or domains. It just doesn't really scale at the cloud level and the automation level. There's been a 100% year-over-year increase in widespread attacks where threat actors are leveraging a zero-day exploit before vendors could patch them. These threats are commonly also used as initial access vectors by attackers. Unit 42 has observed a more than 73% increase in the use of red team tools, such as Cobalt Strike, by threat actors. So these tools are very purpose-built to obfuscate network payloads and emulate real-world traffic to avoid detection. Looking at IPS solutions available today, most utilize signature-based detection mechanisms, and signatures are great at what they do. They can prevent known attacks, but they require visibility into exploit, proof of concepts, and the malware communications. But once we've observed the tactics and techniques used by a threat, research teams can develop sophisticated signatures to prevent it in the future. But this really doesn't address the problem with the patient zero, meaning signatures are kind of always playing catch up, and they do not effectively address zero-day type attacks and evasive C2 channels. Sophisticated red team tools such as Cobalt Strike now empower attackers of all skill levels to evade detections. These types of tools are very easy to use. They can be highly automated, and they're purposefully built to evade signature controls by mimicking normal expected traffic. Most traditional security controls will only see normal network traffic and not suspicious covert communications, and that really just allows the tool to remain undetected. So how must the IPS evolve to solve this problem? Not only do we need the ability to stop known attacks, we need the ability to detect unknown attacks and block them as they're happening in real time. IPS solutions need to be able to detect these zero-day exploit attempts and evasive C2 tools with a very low false positive rate. So in PanOS 10.2, we introduced cloud-based inline deep learning engines to detect and prevent evasive C2 techniques and tactics in real time. We've seen a huge success with this service, specifically preventing over 96% of web-based HTTP Cobalt Strike C2, as well as stopping 48% more evasive command and control traffic over our own industry-leading threat prevention service. During the Nebula release, we told you that this new cloud service would scale with speed in architecture, and we would also try to keep pace with the ever-changing threat landscape. And then we're doing exactly that. With PanOS 11, we've further leveraged the inline deep learning engine to expand the capabilities of advanced threat prevention, the advanced threat prevention service. We're bringing in the ability to detect and prevent zero-day attacks that target unpatched software vulnerabilities via injection attacks like SQL injection and command injection, focusing specifically on inbound threats. Machine learning and deep learning-based detection engines are only as good as the data that's used to train them. Thankfully, here at Palo Alto Networks, we have the largest malware analysis engine in the industry, Advanced Wildfire. So we see anywhere from 5 to 10 times the number of files compared to other industry vendors such as VirusTotal. This allows us to leverage very high fidelity and curated data sets from malware communications observed during cloud analysis and also collected from Unit 42 threat intelligence. This amounts to billions of malicious traffic patterns analyzed over the last decade. So all of this threat data forms the foundation for our machine learning and deep learning models. With these new detection engines, we've observed roughly a 60% increase in the detection of unknown or zero-day type exploit attempts that leverage injection techniques. Palo Alto Networks' Advanced Threat Prevention Cloud Service includes the best-in-class capabilities of blocking known threats, as well as the industry-first inline prevention of zero-day attacks, joining together our existing signature-based prevention capabilities with the new cloud-based deep learning models. PanOS 10.2 launched unknown C2 detection, including detection of evasive hack tools such as Cobalt Strike. PanOS 11 expands these prevention capabilities to zero-day exploits for techniques such as SQL injection and command injection that can result in remote code execution. These models have a very low tolerance for false positives and are also made available in global locations that are monitored continuously for availability and latency. All right, let's get into some technical details on ATP. So looking at today's approach to network security, we have inline controls that are fast and very good at preventing known attacks. They're all largely built on signatures and databases. Unknown attacks are sent to on-prem or cloud-based analysis engines where the data is processed into content that is regularly updated back to the inline control. As previously mentioned, though, this offline analysis takes time, and it's not always fast enough for to stop these newly and highly evasive automated attacks. So this is pretty much the way that everybody's been doing it. This is the way we've been doing it since 2011. And it's worked in the past, but today's attacks are specifically designed to evade these types of signature-based controls. Stopping modern attacks requires an advanced approach to network security. In order to stop highly sophisticated attackers and their tools, we need to embrace artificial intelligence, more specifically, deep learning, not just offline, but inline and at scale. Our inline controls are designed for speed and reliability, but not for the intense processing workloads required to provide real security outcomes from massive data sets in advanced deep learning models. So that's where ultra low latency cloud native computing comes into play by providing verdicts on potentially malicious data flows in a matter of milliseconds, allowing the inline controls to stop the session before it completes. With signature only controls, prevention is based on observed network traffic, and creating a matching signature can take sometimes hours or days. With inline deep learning, we can reduce that to milliseconds, preventing unknown and evasive network threats in real time. So let's get past some of the industry buzzwords and look at how we're leveraging AI. Machine learning and deep learning are very close methods of teaching machines to think for themselves. With ML, a human scientist teaches the model what features to extract from an input to determine the classification of the output. So in the example of a car, the data scientist might tell the model, well, it should have wheels, it should have an engine, and how those two are related are important features to take into account to determine if the input is in fact a car. But with deep learning, the model is specifically built to automatically learn which features are important with no human guidance. So this is extremely powerful when it comes to unknown inputs, such as modern malware, but it really requires two things: very fast processing speed and, excuse me, and a massive data set, a massive amount of data to learn from. So for the data, we've already talked about it. We have over 10 years of threat intelligence within Wildfire, providing our models with billions of samples to learn from. Deep learning's ability to automatically extract features is extremely powerful, but when it comes to detecting cyber attacks, it's the data that's the differentiating factor. So let's look at how this works from a firewall perspective. So we have a firewall with advanced threat prevention enabled. A system is reaching out to a command and control system owned by a malicious actor. And if we've seen this before and we have a signature for it, we're just going to block it, right? So that's the first piece that comes into play. We have a series of pre-filters on the system to understand and filter out potentially suspicious traffic or benign traffic. These can be things, think like the URL category, the app ID. We have some lightweight machine learning models there. But the firewall actually maintains a dedicated channel persistent to the local cloud point of presence. Once we've pre-filtered out the suspicious traffic, it's sent over that channel to our global point of presence and run through our multiple detection models. We'll get a verdict back. We'll send it through some false positive checks, and then we'll ship that verdict back down to the firewall. And this process happens below 200 milliseconds. So effectively giving a verdict on that suspicious network traffic and allowing the firewall to send a reset and block that session from completing. So now that we understand kind of what's going on in the background for ATP's inline cloud analysis, let's look at some real world examples. So here's a really good Unit 42 write-up on some AI techniques that we use to detect evasive C2, specifically HTTP-based Cobalt Strike traffic that's leveraging a malleable C2 profile. The malleable profile dictates how the C2 beacon, which is on the compromised system, talks to the attacker's infrastructure, and it's really highly customizable. And it's built to evade signature-based network security controls. And as I mentioned earlier, Cobalt Strike's being leveraged heavily by malicious attackers, with multiple examples in the last month. Digging into a specific example, here's some HTTP C2 traffic associated with an emotet infection. So you can see there the HTTP header traffic contains several interesting characteristics, but it's a pretty small amount of data that we've pre-filtered out. That's how we're able to send that and get a verdict back so quickly. The machine learning models are very good at looking at small amounts of data and determining a verdict. So some of the characteristics in here that we can pull out as a human analyst that might be suspicious things that the deep learning model keyed off of include the use of a DGA in the URI. There's an IP address in the host field instead of an FQDN, which is what we'd expect. And also the position and the length of the URI is indicative of what we see commonly in command and control. This is an example of an encrypted traffic flow that's attempting to download an additional file. And we see here several suspicious features, including the use of a deprecated version of TLS, a DGA in the certificate SNI, as well as the use of a self-signed certificate. So while this is certainly considered not best practice, each of these things on their own does not constitute malicious traffic. But when seen together by our deep learning models, they determine a malicious verdict. So this is a Unit 42 write-up on a Lokibot variant that we observed at the tail end of last year. The article goes into details about how initial access came through a phishing email with a zip file attached. In the zip file was an ISO file. And when that ISO file is mounted, it contains a PE malware file. And I've done a quick demo here of showing execution of this PE file and advanced threat prevention blocking it. Switch over here. So here's a firewall running PAN-OS 11.0. And we look at our security policy, and we have all of our advanced protections enabled with Iron Skillet recommended best practices. So this includes the inline cloud analysis engine for advanced threat prevention. Switch over to our victim VM, and we've already downloaded the ISO file and mounted it, and we have this suspicious executable file. In the Unit 42 write-up, it talks about how this file spawns a subprocess called the ASP.NET compiler.exe. This is actually the malware running and trying to create a C2 connection back to the attacker infrastructure. We see here, though, we reset the connection, and we have an inline cloud analyzed HTTP command and control traffic detection. Okay. So in this example, we'll look at code injection attempts made against vulnerable web servers. Injection techniques are very common in public attacks. They account for approximately 31% of initial access vectors, second only to phishing. Injection attacks are also on the OWASP top 10 web application security risks, and protecting against known vulnerabilities is commonly considered a foundational requirement for any network security practice. Many vulnerabilities involve obfuscated network requests that can be adopted and augmented in various ways using easily available tools. So here's a view into the data our deep learning model keyed off of. So I'm on the example on the left, we have a previously unknown attack against an IoT device. There are several variations of suspicious commands and common web app attack techniques. On the right is an example of a detection of a Bitbucket vulnerability, CVE 2022-36804. with many suspicious characters that are common to broadly used command injection techniques. So let's look at an example of inline cloud detecting inline cloud analysis blocking a variation of a published CVE. So late last year, there was a critical level security vulnerability found in the common SNMP network monitoring tool Cacti. A lot of enterprises use this open source tool to trend network traffic volume, etc. So in the demo, we're going to use the off-the-shelf Metasploit module for the CVE and show how the signature detects that attack. We'll then follow it with an unpublished variation of the command injection, and you'll see how we get shell access. And then we'll modify our policy to include the inline cloud analysis and rerun that unpublished variation, and you'll see that it's detected and blocked by the inline cloud analysis engine. So let's go ahead and do that demo. Again, PanOS 11.0. Looking at our security policy, as I mentioned, we're going to start with a policy that does not include ATP's inline cloud analysis. So we have vulnerability protection, but the inline cloud analysis engine is not enabled. Switch over to Kali. We see here we've fingerprinted a Cacti server that has a vulnerable version. We're in Metasploit here, and we're going to go ahead and just execute the off-the-shelf published vulnerability. And we can see here there was no session created. Looking at the threat logs, there's a reset on the known signature for the Cacti remote code execution vulnerability. Now, since we're a super lead hacker, we have a variation on that that we've built, and let's see if we can get shell that way. Yep, okay, so we have shell access to the Cacti server, and looking at the threat log, we see no new attacks or no new logs. Let's go ahead and switch up that profile now to include our inline cloud analysis engine. And a little movie magic to get that commit to go through quickly in the interest of time. And now let's go ahead and execute that, that super leet shell command again. And you can see we don't get shell access back. Looking at the logs on the firewall, we'll see a inline cloud exploit prevention, command injection traffic detected, and reset. Hopefully this technical deep dive was helpful, and I'll go ahead and open up for Q&A. Let's take a look, see here. Feel free to add anything to the Q&A here.
So you have about 3 questions that I didn't catch in time. I didn't have the context.
No problem. So let's see. Is there a way to have files analyzed if they're signed with certificates, so they can potentially scan for supply chain attacks? So file analysis, we've got several different techniques in there. We are looking at code signing certificates. So I'm not sure specifically if that's what you're asking about, but during analysis, we have multiple methods with advanced Wildfire to look at malware analysis, and as the efficacy of those methods kind of wanes, we are developing new techniques, and they are constantly being rotated out depending on what we're seeing in the different attacks in the wild. So what's the difference between intelligence and continuous memory capture? They look the same. So let's see. Going back to that slide. A second. I think that's the one. Right. So what's the difference, right? So continuous memory capture, that technique is essentially grabbing memory snapshots, and that's what the little camera at the bottom is indicating, right? So it's continuously grabbing memory snapshots, whereas intelligent memory capture is looking for interesting events and actually capturing the memory at the moment of those interesting events so that we can analyze that memory snapshot. So it's a lot more tenable to be able to consume, in this example at the top, 2 full memory snapshots instead of 6 memory snapshots with continuous memory capture. And just to follow up on that, does this mean that IRMA activates when something suspicious is detected? Yes. And so we have some advanced techniques that are looking for common malware techniques, such as interesting API calls, persistence, those sorts of things that are actually going through and initiating those memory captures so that they can be analyzed. Someone mentioned that the URL is not accessible. So all the slides are going to be provided after the session. So if you're not able to pull up the URL or the QR codes that I had in the slides, those will be available. What specific protections are added to mitigate XDR hooks?
Oh, so I'll take that one.
Okay, yeah.
This is specific to Cortex XDR. It's a technique that's used to redirect the system execution flow to modify software, right? Yes, we do. We actually have a whole module specific to that, but I would recommend that you speak with the Cortex team to go over more details on that. Hope you're still here, Jason.
Yeah, absolutely. So it looks like the URL is a internal URL. So I may have included a wrong URL. So I'll make sure that
I pasted earlier the one that's public.
Oh, okay. Thank you.
I'll repaste it again.
Yeah.
There was an anonymous attendee that pasted the internal loop. I don't know who that was.
Yeah,
I don't know if we have other panelists.
I thought most of my URLs were publicly accessible, so I'm not sure.
No worries.
Maybe there was one that I didn't. So apologize for that. So let's see. Jay asks, in the case of a 0-day attack, will advanced Wildfire not able to detect or detect late? The file will enter the PC. So would the signature be made instantly to block, or will it take time? So the time to signature creation is greatly reduced by advanced Wildfire by doing continuous or doing memory analysis before the code dynamic analysis completes, right? And so we're generating preventions based on that before the file even is completed its detonation. And those protections are streamed down to the enforcement point in near real time. So if you think of a file that's been detonated and is reaching out to command and control infrastructure, we're gaining all the metadata and threat intelligence around that execution, the IOCs, et cetera, and generating content that's being pushed down to the firewall almost instantaneously. So that prevention can then happen very, very quickly on that enforcement point from the endpoint perspective. So if that malware does get through to the endpoint, there is protections on the firewall very quickly in order to understand, okay, was execution on that endpoint successful, blocking any further damage from the attack, and then allowing, incident response to happen on that system. Does AWF run on non-Windows based VMs in our cloud infrastructure? So right now, the AWF advanced features are all focusing mostly on Windows based packed executables. But it's a cloud service, so new features, very easy for us to spin up. How does advanced Wildfire work with Cortex XDR? Great question. So Cortex XDR is an enforcement point that we use.
We've actually answered that question in a.
Oh, okay.
Yeah.
I thought I had a good slide with the enforcement. Here we go. Yeah. So endpoint protection. Yeah. We take samples, detonate them, understand the metadata, push enforcements down to XDR. So it consumes it very similar to how the firewall consumes it. Awesome. Good questions.
All right. Thanks, Thanks, Jason. Looks like we've got all the Q&A covered.